Good morning, everyone. Today we are going to be talking about classifications of matter, the periodic table, and then we're going to move into a discussion of physical states, solid, liquids, and gases, what that looks like at the atomic level, and then move into physical and chemical changes. Okay, so what is chemistry? Chemistry is just the study of matter and energy and the interactions between matter. So what you guys are going to find throughout the course of the semester is chemical changes, physical changes. These occur with energy transfers. We'll have a whole section on thermochemistry, but that is a big piece on why reactions are going to occur or not. And matter in general is just anything with mass and volume. There are two main classifications, a pure substance and then a mixture. So a pure substance is just how it sounds, pure, nothing else added. You can have elements, just like elements off the periodic table, such as copper. Pure meaning there's nothing else in there. There's no other metal, for example, no iron mixed in with that. It's just pure copper. Compounds can also be pure. So water itself, like from a tap, from the kitchen sink, that could have other ions in it, and that would be impure. But a pure compound of water would be just completely pure H2O, nothing else in there. Mixtures can be divided into two categories, homogeneous or heterogeneous. And this is where you're just physically mixing two or more substances that can include elements. So brass itself is zinc and copper, and water and copper can also form a mixture. The air we breathe is a mixture of a bunch of different gases. So homogeneous is when you're uniformly in one phase, one physical state, such as a solid here. Heterogeneous is when you have two or more distinct phases, distinct boundaries. For example, sand and water. You can see that liquid and the solid itself. Okay, so let's take a look, just kind of give you some more examples. Gold, AU, and nothing else. So that's the symbol for gold. That's a pure element. It doesn't get simpler than that in terms of a substance. An element is the simplest substance. Water, pure water, I've already talked about, that's a pure compound. Table sugar, the sugar you add to, say, your food or liquids, that's sucrose. And that's given this chemical formula. So here I'm just showing certain elements, carbon, hydrogen, oxygen, the number, the subscripts tell you how many of those are present in that molecule. And this is actually a pure compound. So just take a look, use what you are seeing here to determine what's the difference between a compound and an element. When you get into sand and water, like I mentioned, you have a heterogeneous mixture. Coffee, milk, and sugar uniformly mixed, that's a homogeneous mixture. Okay, so what is the difference between an element and a compound? The element is the simplest substance. It does have unique properties. This is because each different element has different numbers of protons that can then result in an atom having different protons, electrons and neutrons, giving different behaviors. This is one type of atom. So now I'm throwing in another term. I'll come back to that. A compound you've already seen and hopefully have already decided that's a mix of two or more different elements. So if you have an element, and this one's a gas, it's flying around, so maybe that's neon or xenon. When you want to talk about one of those guys, you could call that an atom. An atom refers to a single guy. Think Adam and Eve. However, when you're talking about something that's bound, and they don't have to be different, they could be the same, but more than one atom bound, we would call that a molecule. So you can have an atom of an element, you can have a molecule of a compound. What's interesting is you can also have a molecule of an element. So there are certain elements, just a handful, like hydrogen, nitrogen, oxygen, all the halogens, which is the second to the last column of the periodic table, these exist as what's called diatomic molecules. So di for two, diatomic, so that's two bound. And so we would call that a molecule of an element instead of an atom. A mixture, we've already talked about, two or more elements and or compounds physically mix. So the air we breathe is actually about 17 different types of substances. That's a homogeneous mixture. It's very uniform, what we're breathing. A solution of sodium chloride in water, that's also a homogeneous mixture if it's all uniform. And what's interesting is you can have some changes with that, where if you heat or boil off the water, you'll come back with a solid salt, the sodium chloride, which you may have seen just from experience coming from the beach or just boiling some liquids. Okay, let us talk about the periodic table. The main groups are shown in red, and here are the first two columns, and then the last six columns here. These are the main group elements. We'll use those a lot throughout the semester, and we'll also work with the transition metals here. The ones we don't see much of are down below, these inner transition metals. And these actually slip into these spots here. So in this third column, when you start getting to these lower rows, this is where the inner transitions slip in. They slip in here, and I should first tell you that the reason why the periodic table is arranged the way it is number one, going left to right and down the periodic table, you're increasing the number of protons. That's the big number on top. We call that the atomic number. So you go from 1, 2, 3, 4, 5, etc. The columns are arranged because they have the same outer electrons. The outer electrons are also called valence electrons. Those are the electrons available for bonding. Those are what accounts for reactivity. So those with similar electron arrangements will be grouped in a similar manner and in the same column. So these guys are unique, and it has to do with how those electrons fill up orbitals within the atom itself, but they slip in right here, and they're numbered the way they are because of their number of protons. But in terms of behavior and reactivity, they're more similar as a group on their own. If you move on to inorganic chemistry, you'll talk a little bit more about the inner transition metals. There's some atomic symbols that aren't obvious, so I do want you to know Fe stands for iron, Zn stands for zinc. Definitely know the main group ones, and I would say the first three rows here of the transition metals. Know those. The ones below, not so much. And even down here, this last row, you don't need to know those or be able to just produce that name or symbol. There are some that don't necessarily seem obvious, like Hg for mercury, and it's because the naming and symbol comes from a different language, maybe German, Latin, or Greek. So there's a good reason for it. For example, Hg comes from hydrogyrum, which means water silver, and if you look at mercury, it's one of two elements that's a liquid, and it's really gorgeous. I've actually seen it in grad school because the thermometer broke, and it's really mesmerizing. It's extremely toxic, so you don't want to handle that, and you will unlikely find mercury thermometers in the labs. Ag is for silver. It comes from argentum, W for tungsten from wolfram, and K for potassium. What you do need to know are the names of the columns, which are groups. So the first column is group 1A. These stand for the alkali metals. And again, this is because they have a specific reactivity. They have one outer electron available for bonding, group 1A. The alkaline earth metals, group 2A, have two outer electrons. The halogens, group 7A, have 7 outer electrons. The noble gas is 8. 8 is what we call filling an octet, and so they're not as reactive. They're pretty much happy with their electron configuration. That's why you sometimes hear noble gases being called inert gases or not reactive. The other thing you need to know is going across, these are periods or rows, and it starts at row 1 with hydrogen, row 2, 3, this is row 4. So row 2, even though maybe halogens here start at row 2, the first fluorine is here, this is a row 2 element. And even though fluorine is the first one in its row, it's not a row 1, it's a row 2. Okay, the alkali metals, these are silvery, very reactive. I'll show a video, probably the first day of class, reacting alkali metal with a halogen. Those are usually really explosive. Hydrogen is included in this group, though it's also considered a non-metal, which is more kind of on the halogen side of the periodic table. It kind of has this dual behavior. Hydrogen is really unique that way. The alkaline earth metals, also silvery, less reactive than the group 1As. Halogens, these are colorful. I'll show some pictures of some non-metals. They can be corrosive. And the noble gases, colorless gases, very low reactivity, and helium and neon don't even combine with others. This is a periodic table that's highlighting the metals, non-metals, and something in between, semi-metals. So here in this reddish color is a staircase of what's in between metal and non-metal, the semi-metals. For those of you colorblind, I wrote them out here. But basically anything to the left of the staircase is a metal. Anything to the right of the staircase is a non-metal. This becomes important because there's different reactivity. Metals combine with non-metals to form ionic compounds. Two non-metals combine to form covalent compounds. So there's different bonding, different reactivity. Metals, you'll be familiar with these. They're solids at room temperature except mercury. They're metallic, they're malleable, so you can bend them. You probably experienced that with certain metals. And they're good conductors of heat and electricity. Non-metals are a lot more different in terms of physical states. So here chlorine is a gas, a yellow gas. Sulfur is this yellow powder. Carbon is graphite, which you've probably been familiar with pencils. Bromine is a liquid, and what's interesting is bromine is kind of a nasty chemical to work with because it can freeze at not so low a temperature, so maybe just with an ice bath, but a little warming above room temperature and it converts to gas. So it's not my favorite thing to work with. Iodine here is like flakes of kind of a silvery, dark silvery color, as you can see here. These are insulators, they're poor conductors. Semi-metals are in between, they look more like metals. Okay, so let's do a concept check. Why don't you guys pause and answer these questions, and then I'll go over them. The first one says, what alkali metal is in period 2? So period 2 is 1, 2, and alkali metal is here, so it's lithium. Halogen in period 5. So fluorine is in period 2, so 3, 4, 5. The answer is iodine. And then categorize the following as metal, non-metal, or semi-metal. Silicon is on the staircase, so it's a semi-metal. Palladium is here in the transition metals, so metal. Rubidium is Rb. It's not Ru, that's ruthenium. So that's a metal, it's an alkali metal. Xenon is here, it's a noble gas, so that ends up being a non-metal. Silver is in the center region of transition metals, that is a metal, and then phosphorus is a non-metal. Again, it's important because later on it'll play a role in you predicting the types of bonding and reactivity as well as naming compounds. The last bit for this video is states of matter and changes within those. You guys are familiar with solid, liquids, and gases, at least on the macroscopic level. There's a fourth that you might not be familiar with. It's a plasma, and these are gaseous ions. We don't cover that, but I wanted to mention it. Physical states are dependent on the temperature and pressure. For example, The planet Saturn is made of liquid hydrogen and has frozen ammonia clouds. Hydrogen and ammonia on Earth are both gases. The Earth's core is composed of both molten and solid iron. So most of the steel that's constructed is iron. Steel is iron. Sometimes it could be doped with other metals. So that's a solid, but you could see depending on the pressure and temperature, you can get molten, which is essentially liquid iron. What I really want you guys to be able to do is go from that bigger macroscopic view to an atomic view and contract your view. So we'll be doing that throughout the semester. That's going to help you connect with what I'm talking about and things you can't really see or touch. So think of solids as, in this case, I'll just show them as balls, and it could be an atom, it could be a certain molecule, or even an ionic compound. These are stacked really nice and neatly in an organized array. A liquid is slightly disorganized, but notice they're still touching. So to go from solid to liquid, you actually have to break up some interactions, right? If you melt ice, you need to add some heat to that. If you completely break up the interactions between those, and again, you're not destroying the actual molecule, for example, you're not destroying water into H's and O's, you're just having them move far apart from each other. And gases are more disorganized, and you could think of them as ping pong balls bouncing around a container. Check out this periodic table. This is a physical state. All the elements in green are solids. So most elements exist as solids at standard temperature and pressure. There are only two liquids, mercury and bromine, and the rest, hydrogen and a lot of these non-metals, those are gases. That can come into play with you just thinking about physical transformations, but also when we write chemical formulas and attach states to those when we write equations. Physical changes, what's important to understand is you do not destroy the compound or the chemical composition. You only affect the form, ice melting, water boiling, changing the form of clay, sugar dissolving. So you're not destroying that compound or the molecule of sugar, you're just dispersing it throughout the water. Physical properties, these can be observed or measured without changing the substance. So some physical properties would be color, volume, melting point, or density. These are reversible. Physical changes are reversible with just a simple change in temperature. So solid iodine, if I heat that up, you go from these flakes to actual gas. So if I had a container of solid iodine and I warmed it up, even with my hand, that's enough to generate some of this iodine gas. If I cool it back down, it'll go back to this solid. Chemical changes are different. This is more significant where atoms actually rearrange. You break bonds and reform bonds. That's the crux of a chemical reaction. This is not reversed by a simple change in temperature. Energy is released or gained. Sometimes reactions don't occur because there's just simply not enough energy for it to occur. Sometimes it'll be accompanied with a new odor, sound, or color. So we have this with wood burning, or iron in steel rusting. Rusting, it occurs when you react with oxygen, and you could go from iron to iron oxide. So chemical properties, these are observed by changing the chemical identity of a substance. Examples are observing the reactivity or flammability or this oxidation state. In rusting iron, to go from just a neutral normal iron to an iron oxide, it changes what's called an oxidation state. We have a whole chapter on that, but it becomes an ion. It lost electrons. Okay, so why don't you pause and answer these questions, and I'll go over them with you, but pause and try these first and determine which are physical or chemical changes. So yellow plastic is melted and forced into a mold to make a yellow toy. That's a physical change. Silver metal tarnishes, forming black silver sulfide. When you're forming a new compound, that's a chemical change. And you notice there is a color change as well to black, and the silver is now combined with sulfide, not just by itself as a neutral silver. Ethanol, this is a type of alcohol, like you're drinking alcohol. Think of it just as a liquid, like water, boiling. That's a physical change, because if you cool it, you could cool it back down to a liquid. No harm, no foul. The ethanol's still the ethanol. A candle burning. This is a little trickier. This involves two changes, physical and chemical. When you actually melt the wax, that's a physical change because you still have the wax there, it's just in a different form. However, how did you create that heat and light? You combusted the wax. The wax is a hydrocarbon. Think of it as a fuel, like a gasoline. You're burning it, and when you combine it with oxygen in a combustion to give carbon dioxide and water, which is classical, regardless of the type of hydrocarbon, that's a chemical change. You broke bonds and formed new bonds. So that's where I want to end today. I will check in with you guys later.